So hello everyone. We are back with another problem to solve in this session. So today I am going to show you how we can solve or how we can answer a couple of questions related to this particular manipulator. Okay, let's start off with frame assignment. I am going to assign all of the frames necessary. Okay, so apparently we have the base frame or the frame that is attached to the first joint. Okay, so we have the first zeroth frame, we have frame 0. Now we have to assign the second one, frame 1. Okay, so we have a prismatic joint, and we know that z1 can be either in this direction or in the opposite direction, right? Okay, let's assume that z1 is directed this way, c1. Okay, now I know that x1 should be perpendicular to both z1, right, and z0. But as you can see, there is no way that I can actually draw an axis that is perpendicular to both of these two z1 and z1 and z0 axes. That's why we are supposed to slide this frame towards left. Okay, if I decide that the origin of this frame is not here but here, okay, which comes from what? Basically, we are just sliding it a little bit so that the x1 can intersect the z0 axis. Okay, I'm basically sliding z1 right here, and my z1 is here. Okay, now I can draw x1, let's say in this direction, right? Now in this particular case, x1 is perpendicular to both z1 and z0, and it intersects the z0 axis. Z0 axis. Okay, that's it. That's it. Okay, fine, fine. What else? Let's move on to the next one. Now we are trying to assign the second frame. I can erase this one. Now the second frame is I can actually put it here. Z1, sorry, Z2 axis can be either upwards or downwards. I'm choosing the upward direction. Now this is Z2. Okay, what about X2? X2 should be perpendicular to both Z2 and Z1, and at the same time, it should intersect the Z1 axis. So obviously, it's going to be something parallel to X1. Now this is X2. Okay, that's it. That is it. And finally, for the end effector, we are we are repeating, or sorry, we are copying the last z axis for the end effector. So z3 will be what the z2 is, right? Let's say this is z3, and x2 should obey by the rule that we've been mentioning from the very beginning. In other words, it should be perpendicular to both z3 and z2, and it should intersect the z2 axis. Okay, now it becomes x3. So this is frame assignment. We have assigned all of the frames. Now we can move on to the DH parameter table. DH parameter table. I know that I have 3 joints, which means that I'm going to have 3 rows for my DH parameter table. All right, let's fill in this table. It's going to be I, joint 1, joint 2, joint 3. Thetas, we have Ds, we have alphas and As. Okay. A. Okay. Now let's start off with theta 1. Now the question for theta 1 is around z0, how much I have to rotate x1, how much I have to rotate x0 so that it can align with x1. So as usual, we are going to take theta 1 because we have a revolute joint. The answer for theta 1 is theta 1 itself. Okay, it's a joint variable. So we have to take the joint variable if needed. Now let's move on to the next one. Theta 2, we are finding this one, this particular one. So theta 2, the question for theta 2 is around z1, how much I have to rotate x1 so that it can align with x2. As you can see, there is no need for any rotation because they are already aligned. So it's going to be 0 degrees right here. What else? We're finding this one. For theta 3, the question is around z2, how much I have to rotate x2, how much I have to rotate x2 so that it can align with x3. Now, again, they are aligned. That's why there is no need for any rotation. 0 degrees for theta 3. Okay, now let's move on to the D parameters. D1. The question for D1 is along Z0 axis, like in this direction, right? How much I have to translate the origin of frame 0, so that it can align with the origin of frame 1. As you can see, we have to move this origin by D1 distance, right? Okay, so that it can come up here. Okay, that's it. The answer is D1. D1. The next question. Well, we are finding D2 now. Now, the question for D2, well, along Z1 axis, how much I have to translate the origin of frame 1 so that it can align with the origin of D2? The answer is D2 itself. We have to move from here to here. By what distance? D2. So D2 is to be written here. Now, D3, we are finding this one now. D3. Now, along Z2, how much I have to translate the origin of frame 2 to align it with the origin of the frame 3? The answer is D3, as is clear. Okay. Now, D parameters are derived as well. Let's move on with the alphas. Alpha 1. Let's find the alpha 1 parameter. The question for alpha 1 is around x1, how much I have to rotate z0, right? How much I have to rotate z0 so that it can align with z1. First things first, I have to know the exact positive direction of rotation around x1. So my right thumb is going to be in this direction, my right thumb, okay? And the curled forefinger shows the direction of positive rotation, which is this way, right? Yes, this is positive direction, okay? Now, Z0 is here. Now Z1 is right here. So obviously we are supposed to flip it in this direction, right? By 90 degrees. And this is positive 90 degrees because the rotation, positive rotation direction is this one. Okay, this is Z0, right? And I'm rotating it by 90 degrees in the positive direction according to my right hand curling rule. Now it's going to be pi by 2, 90 degrees. Let's move on to the next one, alpha 2. Alpha 2 is right here. Okay, alpha 2. The question for alpha 2 is around x2, how much I have to rotate z1 so that it can align with z2. Once again, we have to define the positive direction of rotation around x2 axis. Now, my right thumb is here. The four fingers curled shows the positive direction of rotation. Again, this is this is in this direction, just like what happened here. Okay, so it was here. Z1 is right here. Now I am actually kind of lifting it up. So positive direction was that one. This is positive direction, but I'm lifting it upwards so that it can align with Z2. That is the reason why we have to write pi by 2. Okay? Now, what else? What else? Alpha 3. What about alpha 3? Now, the question for alpha 3 is, around x3, how much I have to rotate Z2 so that it can align with Z3? They are already parallel to each other. That's why they do not need any rotation. We do not need to rotate Z2 by any angles. That's why it's going to be 0 degrees for alpha 3. Now, let's move on to A variables, A parameters, sorry. Now, the question for A1, we're talking about this one. The question for A1 is, along X1, like in this direction, right? Along X1, how much I have to move the origin of frame 0 so that it can align with the origin of Z of frame 1. They are already at the same point along this this X1 axis, right? At 0 point, right? That's why there is no need for any translation. 0 meters right here. Okay, the question for A2. The question is X2, along X2 axis, how much I have to translate or move the origin of frame 1, okay, to align it with the origin of frame 2. Again, these 2 points, these 2 origins of these 2 frames are at the same point of this axis, which is 0, point 0. So there is no need for any translation. 0 is supposed to be written here. What else? A3. A3. The question for A3 is, along X3, how much I have to move, how much I have to translate the origin of frame 2 to align it with the origin of frame 3. Again, these 2 points are at the same point of X3 axis, so there is no need for any translation. That's why we have to write 0 meters right here as well. So this is the DH parameter table. DH parameter table, from which you can find the direct kinematic equations, right, to get the homogeneous transformation matrix of frame 3 with respect to frame 0. Okay, right? That's it. That's it. So one of your tasks for this problem is to define or is to assign the frames, which has been done already. Then DH parameter table, which is done as well. What else? And Jacobian matrix. The next task is to find the Jacobian matrix. Okay. Now, I am going to show you two methods, right? First method is this one, using direct kinematic equations, all right, and the H parameter table, right? I can actually derive my Jacobian matrices, or I can use geometric inspection, right? I can use geometric inspection to find whatever I need to derive the Jacobian matrix for this particular manipulator. Okay, I think, well, I feel like it's better to start off with the geometric inspection. All right, let's start with geometric inspection. Now, we have to have a look at this picture from different angles. All right, let's start with the top view. Okay, this is my eye. I'm looking at this picture from above, right? This is the angle of view from top. Okay, now when I see this picture from above, I see y0 and x0 axis. Let me draw them down right here real quick. This is y0, this is x0, y0 and x0. Okay, what else do I see? I see the top of this revolute joint, right? Then I see this length. I cannot see this one because it's just it's a perpendicular line towards my eye, right? Then I see this one, all right? I can see x1 and z1, these two axes. I can see the top of this prismatic joint and x2 axis as well, and x3 axis as well, and z3. No, I cannot see z3. That's it. So what I'm going to do is slowly writing them down or drawing them in a planar view. So the first thing was the revolute joints top view. Okay. Now the challenging part, the trickiest part here is to take the angle theta 1 into account. All right. Now, uh, first of all, let's see what is the positive direction of for theta variable. Okay, positive direction of rotation around z0. Okay, again, my right thumb is pointed to upwards, right? And the curled forefinger shows the positive direction of rotation, which is this one, right? Yes, this is the positive direction of rotation around z0. Okay, so z0 is here towards me. In this particular case, it's towards me according to the right hand rule, right? And it turned out that this is the positive direction of rotation. All right. Now, now, uh, the question can arise from the fact that we usually uh, draw this link, which is seen to this eye, right? Now, this link should be here or here or somewhere else. Now, this is the trickiest part. Now, to define this, let's say, to determine this, let's say, this angle theta, right? Which is, what is theta 1? Theta 1 actually shows from here. How did we find theta? Theta 1 actually shows the angle, okay, that user should rotate the x0 to align it with x1. Okay, I rotated x1 by theta 1 degrees to align it with x1 axis. Okay, so I am trying to like generate a scene, right, which involves x0 and x1, and the angle between these two axes is going to be a theta 1. Okay, let's assume that this is x1. This is x1, right? Now, and the perpendicular line to it will be z1. Okay. Okay. I just drew these two axes, nothing else. These two axes, nothing else. Okay. So just you try to use your imagination. Try to use your imagination. Now it was previously here, right? Now it's somewhere here. Somewhere here. If x1 is here, it means that z1 is supposed to be here, right? Because we made some changes with the angles. Okay, if z1 is here, z1 is attached, let's say roughly speaking, to this link, right? To this length. If z1 is rotated, it means that previously this link should have been rotated, right? So z1 and this length of the link, which is d2, they are aligned. They are on top of each other, right? If one moves, or preferably if this link moves, z1 moves with it. Okay, so this is going to be the length d2, this particular link. Okay, and I can see the prismatic joint and everything on top of it. Now this is point P. This is point P. Okay, that's it. That's it. What else? Yes, exactly. That's it. This is point P. Now, have a look at that. Now, what is theta 1? Now, where should I place my theta 1 now? The definition of theta 1 is around z0, which is towards me, towards us, right? Around z0, how much I have to rotate x0 to align it with x1? The answer is theta 1. Now, this particular angle is positive theta 1. So this is how we, you know, relate x0 and x1 in a two-dimensional space, or plane, two-dimensional plane. Okay, this is how we place the theta 1 angle. Yes, that's it. I think we can move on now. Now this is my representation for the geometric inspection. Now, why did we use why did we use this geometric inspection? Basically because one of the tasks in the exam will be to find the Jacobian matrix. Okay, I think I overlooked one point, because previously and before that, I have to provide the formula for Jacobian matrix, geometric Jacobian matrix. Let's do it now. It doesn't matter. J of Q, let me write it this way. J is equal to, it consists of two parts, JP and JO. Now, we have three joints: revolute joint, prismatic joint, prismatic joint. Now, for the corresponding, let's say, joints, I have different formulas along different columns, right? Now, the first one is going to be Z0 cross product P minus P0. Now, did you understand why we used geometric inspection here? Because we have to find the position vector of this particular point P. Now, this is vector P, position vector. P0 is given, Z0 is given. We know these two values. Now, here we have Z0. For the second joint, which is a prismatic joint, I have Z I minus 1, which is 2 minus 1, Z1, right? And for the angular velocity contributions, I have 0 here. Now, finally, for the third joint, which is a prismatic joint as well, it's going to be Z3 minus 1, which is Z2, and 0 here. Okay, now this is the formula for the Jacobian matrix of this specific manipulator. Okay, now I know Z0, I know Z0, I know P0, but I do not have any idea about Z1 and Z2. Now this is the question. And this is the reason why we have to use geometric inspection here to find P, the vector P. Okay, let's start with P. Okay, by the way, let me put it down here. Z0 is equal to 0, 0, 1. Okay, what else? P0 is equal to 0, 0, 0. These two values are automatically written. Okay, whenever you try to find the Jacobian matrix, just like that, you know the values for Z0 and P0, they're automatically given. So we know their values. They are by default supposed to get these values. Okay, let's find P from geometric inspection. Now we have this triangle, right? It's a triangle, right? Triangle. So it's PX. Now this is PY. Okay. Now from this triangle, I know that this angle is pi by 2 minus theta 1, right? And I know this side, which is d2 times sine of pi by 2 minus theta 1. In other words, this is, and it gives me cosine of theta 1. So I can write it d2 times cosine of theta 1. Okay. What about px? This side of the right triangle. It's going to be px is going to be d2 times cosine of pi by 2 minus theta 1. And cosine of pi by 2 minus theta 1 gives me sine of theta 1. So it becomes d2 sine theta 1. But pay attention, the signs, it's positive point of this axis x0, right? But this is point 0, right? This is the y0 axis. And above, beneath this point, we have negative, right? Negative values. So that's why it's going to be, Py is going to be minus d2 cosine of theta 1. Now, Py is equal to, well, d2 sine of theta 1. Py is d2 cosine of theta minus d2 times cosine of theta 1. And what about pz? Can I see it from here? pz is right here. This is z0 axis, right? Everything is taken according with respect to this base frame, right? So the point P, the component or the projection of point P on this axis is going to be what? This particular length d1 plus this particular length d3. Okay, d1 plus d3. d1 plus d3. So P is given as well. P is given as well. What else? Z1. Let's try to find Z1 because we don't know it either. Z1. Again, using geometric inspection. Now, bear with me. If you're not so confident enough to use geometric inspection for Jacobian matrices or direct kinematics and stuff like that, do not worry. I am going to show you how we can use this matrix, to repeat or to just solve this problem, to derive the Jacobian matrix. Okay, don't you worry, just bear with me. Let me finish it real quick. And I'm about to go, get back to this problem using another method, which is conventional direct kinematic equation method. All right, where did we stop? Yes, we were talking about Z1. First of all, let's see where Z1 is. Z1 is right here, right? This is Z1. Again, this small triangle gives me everything. Everything. Have a look at that. This is, let's say, vector Z1, okay, which is a unit vector whose length is 1, right? And I have this triangle. Right? And the projection of Z1 along X0 is this one. And projection of Z1 along Y0 axis is this one. Let me put it this way: Z1Y and Z1X. Okay. So by simply finding this side of this triangle gives me Z1Y, and this side will give me Z1X. It's so simple, but take into account that the direction of Z1Y is opposite to Y0, which is upwards, right? But luckily, Z1X and X0, their directions actually align. All right, so we are good. This angle is clear, is given, which is pi by 2 minus theta 1. So that's why it's going to be Z1X is going to be the length of this side, which is 1, times cosine of pi by 2 minus theta 1. Okay, let me put it this way: cosine of pi by 2 minus theta 1. What is Z1Y? Z1Y is sine of pi by 2 minus theta 1. Okay, so this gives me what? And of course, the projection of Z1, which is this one, Z1 vector, along the, on the Z0 axis is 0. So the final answer is going to be, well, sine of theta 1, yes, minus cosine of theta 1 and 0. Yes, that's it. That's it. Now let's move on to the next axis. So this is Z1, C1 sine 1 minus C1 and 0. What about Z2? What about Z2? Now Z2 is going to be, let's have a look at that. Z2 is here, right? Z2 is right here. As you can see, this is parallel to Z0. So no matter what you do to rotate it, translate this joint and stuff like that, whatever you do, Z2 is always parallel to Z1. So they are equal. So it's going to be 0, 0, 1. Okay, that's it. That's it. I think we are good to go. Okay, according to this, let's say, vectors, right? I can actually find J by substituting this value to this matrix. So as a result, we get J is going to be 6 by 3 matrix D2 C1 and D2 S1 0 0 0 1. What else? Minus S1 C1 0 and 0 0 0. What else? What is Z2? 0 0 1 and 0 0 0. Now this is the Jacobian matrix for this manipulator. Okay. Now the next question tells or asks us to find the singularity point, and we know that the singularity points of any given manipulator can be found by equating the determinant of the linear velocity contributions of the Jacobian matrix to 0. Okay, all you have to do is to solve this problem, and basically, it means that we just take this part, that's it, and find the determinant of this part. So it's going to be 1 times minus 1 over 3 plus 3 times D2C1, D2S1 minus S1C1. Okay, and we get, well, D2 times, again, cosine of theta 1 squared plus sine of theta 1 squared. So D2 is going to be 0. Now this is the singularity point for the given manipulator. That's it. Now this is it. Now, at the very beginning of the video, I told you that we can use another method, to realize this procedure. And this is using this technique, this matrix. Well, I just realized that I made a typo here. When I copied this part here, I made a typo. So it should have been what? Well, sine of theta 1 minus, oops, okay, minus cosine of theta 1, 0. Okay, so I made the same mistake here as well. So it's going to be positive, it's going to be negative. So AD minus BC is going to be like, minus thing right here. So again, the same thing. Luckily, we haven't really digressed that much. Anyways, I think everything is fine, right? So far, so good. Now let's try to do the same thing in terms of Jacobian matrix. I'm talking about Jacobian matrix for using the this particular matrix. Now let me copy it. Let me copy this. Sorry. Copy it. All right. Okay. Let me put it right here, and I'm going to need the H parameter table, obviously. Okay. The H parameter table. I'm gonna need this one too. All right. Now, again, forget about position vector. Geometric inspection. If you are not so confident about that, just forget about this. Let's say we have never covered it. let's say we have never seen any geometric inspection, stuff like that. And let's start from the very beginning. So you are supposed to find J, right? Which is Z0 cross product P minus P0 and Z0 here for the first revolute joint. Then we have prismatic joint, which comes with Z0 and 0, and I mean Z1 and Z0, Z2 and Z0, oh my God, 0 for the last prismatic joint. Now, like starting from this formula, okay, let's use the matrix, this matrix, to find Z1, Z2, P, what else? That's it. These three vectors should be found using this matrix. Now, this is your task. Like, you are not supposed to make any mistakes, like, because you are not relying on your intuition, but basic computations of matrices. Nothing else but computations, okay? That's why you are less likely to make mistakes. All right, so I know Z0. Z0 is 0, 0, 1. I know P0. This is 0, 0, 1, 0, 0, 0, right? Now let's find, for example, P. Well, P can be found from this matrix, the homogeneous transformation matrix of frame 3 with respect to frame 0. It gives you the vector Z3 and it gives you the position vector P, the same P that we are going to need. What about Z1? Z1 can be found from the matrix A1 to 0. Okay, and this matrix, this 4x4 matrix, gives me Z1, the axis Z1, I mean the vector Z1 that I use here, and P1. All right, P1, which is the origin. Have a look at that, which is this point with respect to the base frame. What else? Z2 can be found from A2 to 0. It gives me the vector Z2 that I'm going to need here, and P2, which is not going to be needed for this particular matrix. Okay, I can find this information, but I don't need them because we don't see them here. I'll need P, I'll need Z1, and I'll need Z2. And to get those, we have to find these three matrices. Using what? Using this matrix formula. Let's start from the very beginning. Now, you have to collaborate with these two pieces of information, like this matrix and the de Navier-Hartenberg parameter table. Okay, in case you want to find A1 to 0, right, you have to take the first row. Okay, now this is theta 1. This is I, which is 1, theta 1, D1, alpha 1, A1. And you see this formula. So instead of like I, we substitute 1, to I, right? So it becomes 1 minus 1 becomes 0, right? So A1 to 0 equals, instead of theta I, you know theta 1, sine of theta 1, right? Minus sine of theta 1 times alpha 1, theta 1, alpha 1, alpha 1, theta 1, alpha 1, theta 1, alpha 1, alpha 1, A1, theta 1, alpha 1, theta 1, D1. See that? That's it. All you have to do is to use the first row of the DH parameter table. Now let's try to do it. Now what do we have? A 4x4 matrix. Instead of theta 1, I can write theta 1 itself, right? So cosine of theta 1, then sine of theta 1, 0, 0, minus sine of theta 1 times cosine of alpha 1. What is alpha 1? Pi by 2, right? So cosine of pi by 2, let me put it this way, cosine of pi by 2. This is 0, right? So I can simply write 0 here. Okay, then again we have cosine of alpha 1 here, and I know alpha 1 is pi by 2. Again, this one becomes 0 as well. 0. Sine of alpha 1 is, I'm talking about this one. Sine of alpha 1 is 1 because sine of pi by 2 is 1. And this 0. Simply put 0 here. All right, let's move on to the third column. Okay, theta 1 is theta 1. So sine of theta 1 times, what about sine of pi by 2? This is pi by 2, right? Sine of pi by 2 gives me 1. So sine of theta 1 times 1 gives theta, sine of theta 1. What else? Minus cosine of theta 1 times sine of pi by 2 again. It becomes minus cosine theta 1. Then we have cosine of pi by 2 because of that, right? I have 0 here and my typical 0 here. Okay? 0. Now, A1, what is A1? 0. It's going to be 0. A1, again, 0. This is gone as well. D1, what is D1? D1 is D1, and 1 is right here. So 0, 0, D1, and 1. Okay, so this is the homogeneous transformation matrix of frame 1, right, with respect to the base frame. It basically shows you, this matrix basically shows you how this frame is oriented with respect to the base frame. Where is the origin of the frame 1, right, with respect to the base frame? It tells you all of these pieces of information. All right. So, and what is really interesting is from a 1 to 0, from this matrix, you can derive Z1. This is Z1. Feel me? This is Z1, obviously. Now this is P1 that you have to use in the formula for the Jacobian matrix. So you know Z1 now. This Z1 is this matrix. Okay? So you deduct this information. Z1, I mean, you derive this information from this matrix, homogeneous transformation matrix. Sine of theta 1 minus cosine of theta 1 and 0. Let's check if we get the same result from the geometric inspection. So this is Z1, right? Sine of theta 1 minus cosine of theta 1 is 0. Let's see. Sine of theta 1 minus cosine of theta 1 is 0. The same thing. The same thing. Okay? So we are good. So now I know what is Z1 as well. I know Z0, I know P0, and I know Z1. Let's move on and find A2 to 0, because I know that from A2 to 0, I can get Z2 as well. And at the same time, I know that A2 to 0 is equal to what? A1 to 0, which is already given, right? Times, according to the composition rule, A2 to 1. We don't have it, but we can find it using this matrix. Okay? Now, from here, I can find A2 to 1. And you know how we can do it? Simply choosing the second row of the homogeneous transformation matrix. Denevert-Hartenberg parameter table, DH parameter table. Okay, so let's see what happens. So we have theta 1. No, it's a 0 now. It's going to be, so it's going to be what? Well, 1 is going to be 0 because theta 2 is 0, right? You have 2 here, 2 minus 1, so it gets A2 to 1, right? So 0, 0 minus sine of theta 1, 0 from 0. Cosine theta 1 is 1. Cosine of alpha 1, have a look at that. Alpha 1 is minus pi by 2. So it's going to be minus 1. 1 times minus 1 becomes minus 1. Then we have sine of pi by 2. No. Sorry. Cosine of pi by 2 actually is 0. So it's going to be 0 as well. So sine of pi by 2 minus pi by 2 is going to give us -1 and 0 here. Sine of 0 gives us 0. Sine of 0 here, no, it's actually 1 times minus 1, right? -1, right? Why -1? Because sine of alpha 1. What is alpha 1? This is alpha 1. So sine of minus pi by 2 gives us -1 times the minus from the equation. Look at that, minus from the equation times cosine of 0. Okay, so we get -1 times -1, which means we get 1 here. So cosine of alpha 1 is, sorry, alpha 2, sorry, minus pi by 2, it becomes 0 as well. 0 we have here. So cosine of theta 1. A1 is 0, that's why it's gone. This is gone. This is gone as well because A2 is, look at that, A2 is 0. These two are gone. D2. What is D2? D2 is D2. Okay, D2 here. That's it. So let me just transfer this information. So we have 1, 0, 0, 0. I hope I actually substituted correctly. 0, -1 and 0, 0, +1, 0 and 0, 0, 0, D2 and 1. All right, that's it. It basically shows how the second frame is translated and rotated with respect to the first one. Okay. Now, but we haven't really found A2 to 0 yet. We haven't found it yet. So from that, I know that A2 to 0 is going to be equal to like product of this matrix times this matrix. Okay, product of these two matrices. Now let me do it real quick. So it's going to be cosine of theta 1. Then we have sine of theta 1 here. Then 0, 0, 0, 0. What else? 0, 0, 0, and 0 here. Okay, then we have 0, 0, minus sine of theta 1, 0. Then 0, 0, cosine of theta 1, and 0, 0, 0, 0, 0, and 0, 0, 0, 0 here. What else? Well, okay. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0. That's it. Okay, and finally, 0, 0, D2S1, right? And 0, 0, 0, minus D2C1, and 0, 0, 0, 0, D1, right? I guess. Let me see. Hold on. Hold on. Okay, 0, 0, 0, D1. Okay, and 0, 0, 0, 1 here. Now, finally, we have the matrix A2 to 0, which can give me Z2. Where is Z2? This is Z2. Okay, now that is Z2 without using any geometric inspection. Okay, this is Z2. Let me put it this way: Z1, Z2. Let's check if it's right. Let's check. Z2 here is 0, 0, 1, right? 0, 0, 1. And using the conventional method, I get 0, 0, 1 as well. Okay, so everything is fine so far. Now, let me put it this right here. Z2 is 0, 0, 1, 2. Okay. Now, what about this one? Just like in this matrix, this is P1, right? Now, this is P2 as well. So sometimes you might have some problems that you will have to use this vector as well, particularly if you are considering revolute joint as a second or third or fourth, I don't know, joints. Okay, I think everything is fine. Everything is absolutely fine. Now, shall we move on? Yes, let's move on. Now, finally, we will be uh, taking the last row, okay, the third row of the DH parameter table, right, to get a 3 to 2 as the last final step. Okay, I is 3 now. It's going to be 3 minus 1. So we get a 3 to 2. And it's equal to, using the last piece of information from the DH parameter table, this one, DH parameter table. Okay, let's substitute all of the variables to this matrix. So theta 1 is 0. So it's going to be 1. Okay. I hope the internet is restored, because I lost my access to the internet just a while ago. Okay, I hope I really missed a lot. So theta 3 is 0. That's why this is going to be 1. This is going to be 0, 0, 0. Then minus sine of 0 gives us 0, so it's gone. This is gone. So cosine of theta 1, theta 3, 1 times cosine of alpha 3, which is 0 as well. It's going to be 1 as well, 1 times 1. So sine of alpha 1 is 0. Alpha 3, sorry, is 0. That's why it's going to be 0 as well. So this is going to be 0 as well. This is going to be 0 as well, because we have sine of 0 here. Then we have cosine of alpha 3, which is 0, and cosine of 0 is going to be 1, and 0 here. A1 is 0, 0. D1, sorry, D3 is what? D3, and 1 here. Okay, let's copy it. Let's just copy this one. So A 3 to 2 is going to be 1 0 0 0 0 1 0 0 0 0 1 0 0 0 D3 1. Let's try to understand this one, at least for this for the moment. We have a 3 to 2, right? What does that mean? It means that the matrix, the following matrix, this one, shows us how the third frame has been rotated with respect to the second frame. How? It's an identity matrix, right? If a rotation matrix is an identity matrix, it means that there has never been any rotation. Let's see if it's right. Look at that. We have this, and we have identically the same frame here. It hasn't been rotated. So that's what the rotation matrix is, an identity matrix in this particular case. 1, 1, 1, and zeros. Okay, I think I messed up, okay? So it just shows that there has never been a rotation from frame 2, all right, to frame 3. Or rotation matrix of the frame 3 with respect to the second one is an identity matrix, which means that there has never been a rotation. But there has definitely been a translation. Have a look at that. The origin of the second frame has been moved by D3 along what? Z2. Okay? Along this direction, let's say. Let's see if it's written here. Yes, it's written here. See that? It has been written here. So mathematically, everything tells us something. Now, finally, oh, no, okay, I cannot derive anything here yet. So all I have to do, have a look at that. I am supposed to find this matrix to get Z3 and P. And I don't need Z3, but I definitely need P, because I'm going to you know, I'm going to need it in the Jacobian matrix, P. Now, P can be derived from this matrix, the transformation matrix of the third frame of the end effector, this one, with respect to the base frame, the direct kinematic equation, right? Now, so this is going to be A1 to 0 times A2 to 1 times A3 to 2. I have A1 to 0, I have A2 to 1, I have A3 to 2, okay? Right? Now, so I know this product because I used it here. Where is that? I used it here. I know this product. Because previously, to get the matrix A2 to 0, I multiplied this matrix by this matrix. The same thing, right? So I know this one is going to be equal to, well, C1, S1, 0, 0, minus S1, C1, 0, 0, 0, 0, 1, 0, D2, S1, minus D2, C1, D1, 1. Okay? Times, this is the same thing, guys, times A3 to 2, which is this one. Okay? 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, D3, and 1. Okay, let's multiply these two matrices, and we get what? C1 here, S1, 0, 0, minus S1, C1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, D2, D2S1, 0, 0, 0, minus D2, C1, 0, 0, D3 plus D1, 0, 0, 0, 1. Okay. Now, since I have this matrix, and I told you that this matrix can give me P and Z3, let's see where they are. Now, this is Z3, and this is the position vector of the end effector's frame or body frame with respect to the base frame that I'm using here in this formula. Okay, let's see if we have got the same result using the geometric inspection. Where is that? P. Absolutely right. The same result. D1 sine of theta 3 minus D2 cosine of theta 3 D1 plus D3. See? You see that? We get the same results. No matter what you do, you are supposed to get the same correct answers only. Okay, so you have everything. You have everything, right? So Z0 is given. P is given. P0 is given. Z1, where is that? Is given. Z2 is given. Z0 is given. 0 and 0 are just clear. They are just three such vectors, zero vectors, nothing else. I think everything is perfectly fine. So all you have to do is to substitute these vectors to this formula and get the Jacobian matrix from which you can find the singularity point. That's it. Nothing else. Nothing else. Nothing else. Okay? Okay. I hope you enjoyed it. I hope it was helpful enough. Again, I'm repeating myself. The gist, the point of such a question is to find the Jacobian matrix. All right? I'm not going to specifically ask you to use either a geometric inspection or, matrices. It's all up to you. Whatever suits you, go for it. I don't really care. But give me the explanation, okay? If you use matrix, let's say, method like that, I have to see it. If you use geometric inspection, I have to see it as well, okay? So have a good day. I hope it was helpful. Talk to you soon.